Y27 quantum bound states. In Newtonian mechanics, position and momentum represent the phase space, and once the two dynamic variables are determined, any physical variables are determined accurately. Unfortunately, quantum mechanics is a kind of wave mechanics. And as we have studied earlier, momentum of a particle is represented by the wavelength of the corresponding wave, so-called matter wave. And in order to define the wavelength, it should be a wave, and its wave function squared is the probability of finding the particle. Lambda is fixed, then P is completely determined by this. However, once you know the momentum exactly, there is no way to identify the position of a particle because this sinusoidal function is propagating all over the space. This is closely related to the uncertainty principle that the configuration, this coordinate in the configuration space and momentum in momentum space, these two are not to be determined simultaneously accurately. That's the great absolute difference between the Newtonian mechanics based on point particle description and wave mechanics. Okay. Photoelectric effect and Compton scattering indicate that the quantum mechanics must satisfy the conservation of energy and conservation of linear momentum because the derivation in theoretical side is based on the four momentum conservation. Four momentum has the time component, the energy, and the other three spatial components represent the linear momentum. Hence, we can make an educated guess that the fundamental conservation laws of Newtonian mechanics are also satisfied by quantum mechanics, sure. While the electromagnetic energy density describes the differential electromagnetic field energy in is wrong, d cube x, and d cube x is measured. This is energy density, so we have to multiply this. Okay. So we would like to extend our understanding of electromagnetic field. The intensity of the electromagnetic field energy is to be interpreted as the probability of finding a quantum mechanical particle whose wave function is psi tx, and the probability of finding that particle in space within this region is the absolute value squared of the corresponding wave function multiplied by the volume element. In addition, quantum mechanics has an operator equation that the wave function must satisfy such kind of a wave. It is generalized wave equation, that is operator equation. For example, momentum operator exists. this e to the I kx minus omega t, this is a wave function. Then how can I read of the momentum? That is h bar k. That is to take the derivative with respect to x. So we have a momentum operator applied to the wave function. Then I would get the number that corresponds to the momentum comes from de Broglie wavelength. So wave function is usually a sinusoidal function or the linear combination of them, such as the equation of motion for harmonic oscillator, damped harmonic oscillator. We had two linearly independent solutions, and the linear combination of them would generate the general solution, something like that. So we consider two cases the same, except that the direction of propagation is opposite. The momentum operator is gradient multiplied by h bar over I. If I take an action of the momentum operator to a wave function, if it is a correct wave function, then the shape of the function must be the same, except that it produces as a coefficient the momentum. This exponential function gives birth to the number. This is momentum, but this function keeps the same form even after applying the momentum operator. So we say this is eigenvalue. What eigenvalue? X operator's eigenvalue. Now this X is momentum P. We say this is a momentum eigenvalue. And the wave function that keeps the momentum eigenvalue is the momentum eigenfunction. Wave function whose eigenvalue is well defined, then it is an eigenfunction, eigenvalue. Eigen means it is German, it is characteristic, such as omega 0 that we pull out from the simple harmonic oscillator, something like that. We had another function, psi 2, that produces negative of h bar k, so its momentum eigenvalue is this. In a similar manner, I can construct the Hamiltonian. Hamiltonian is nothing but the total mechanical energy. If it is a free particle, then the total mechanical energy is nothing but the kinetic energy. And momentum squared is a Laplacian, and we divide this one by 2m, and this minus h bar square comes from the square of linear momentum operator. Therefore, the Hamiltonian is applied to the same wave function. We get the Hamiltonian, the total mechanical energy. In this case, it is a free particle, so kinetic energy. This function has the same form even after being applied by the Hamiltonian operator. This one also gave the momentum, linear momentum, and this one also gives the kinetic energy. Although x and t are not to be determined simultaneously, p and p squared over 2m, this kinetic energy and linear momentum, they can be determined simultaneously. That's the reason why we have the same wave function even after being applied by the two operators, that is either linear momentum or kinetic energy. We find that the two wave functions psi1 and psi2, they have the same energy. We say this energy state is degenerate. You remember we have double root solution for damped harmonic oscillator when the 1/2 of gamma is equal to omega 0. We had the double root in that case. Just like that, the momentum h bar k and minus h bar k, even though the two momenta are different, their resultant kinetic energy are the same. So we say it is a degenerate. So let us simplify our analysis into one dimension. The probability of finding a particle in one dimension, so interval is given in here, we multiply the square of the absolute value of this. What is the absolute value of this? That is 1. So it is 1 all over the space. It is 1 is missing, dx is missing. 1 times dx. So the probability of finding a particle is even in any interval. So proportional to the width of the interval. Momentum operator in one-dimensional motion is h bar over I, partial derivative with respect to x. As expected, this wave function is an eigenfunction of the linear momentum because after applying this momentum operator, we obtain h bar k, the eigenvalue, but the shape of the function doesn't change. So this is an eigenfunction. Invariance of the frequency of the electromagnetic wave at the interface of two media, we remember that derives the Snell's law. Snell's law can derive from postulate the continuity of wave function. Wave function doesn't break at the interface, right? The continuity of wave function allows a finite discontinuity of momentum of a particle. Yes. Because, for example, even though it is not broken, the wave, this and this wave, they meet together. It is not broken, but this lambda and this lambda different. That means from different lambda, we obtain different h over lambda prime and different values for h over lambda, different momentum. So at the boundary, left and right, we might have a discontinuity in linear momentum. That is true when I bounce a ball against a hard wall. Velocity was to the right, but right after the collision, it flips the direction. So there is a point at which the linear momentum has discontinuity. So discontinuity in linear momentum, you don't have to be unhappy about that. It is normal. Our interpretation of the wave function in this manner was only possible after the establishment by Max Born. He is the very person who introduced this idea, and we keep using this. And it is a well tested experimentally too. Haha, there is a special notation introduced by Dirac, and that is called cat. Perhaps you are familiar with the now matrix, and when you multiply the column vector and you multiply a row vector to a matrix, it is usually written in this form and transposed. So Dirac's cat at broad notation is nothing but this and this. And this transpose is written in this form, and this column vector is written in this form. So we say it is a bra and cat and bra cat is a collective word identified to represent this transpose and column vector. Actually, Heisenberg introduced for the first time of the idea that quantum mechanics is described by a matrix algebra. Therefore, when we deal with a matrix, it is convenient to make use of bra and cat notation, especially when you consider a continuum wave function, or even if it is not a continuum case, wave function is well defined. If we introduce this kind of a strange idea, the wave function is actually projection of a quantum mechanical state that is mathematically abstract, but if I want to measure this particle at some point, we need to find the absolute value of this wave function squared. Okay? To do that, we first point a position at which the particle is being described. So we introduce this strange notation with the cat that represent the quantum state and a special bra that represent the position, collection of position. It is something like a completeness relation. For example, we have a vector and we expand this in terms of Cartesian coordinates. And this is nothing but E1 multiplied by E1 dot V vector and so on. And in fact, it is nothing but E1 cat and multiplied by E1 bra and this. Because when we collect the first Cartesian component from a vector V, it is usually written in V1, V2, V3. And when I collect this, what I do is multiply unit vector 1, 0, 0 as a transposed form. Therefore, this kind of algebraic expression looks looks very busy, but this cat and bra notation is a very easy to identify. This is a transpose to pull out the scalar product, and this is to multiply the column vector, something like that. As a result, the completeness relation in the Euclidean space can be simply expressed in terms of EK, cat and bra, sum over K runs from arbitrary dimension. So this is actually the identity operator. But I don't want to go very detailed about this theory because we are elementary students. Anyway, this is a state cat, and wave function is a projection onto space. And actually what we know that the wave function squared integrated over space is one introduced by Max Born. And why don't we write this one? This is actually the complex conjugate and this function and this. And we can rewrite this one as an integral of dx over dx a simple abbreviation of this representation because we promised to write it in this way. This is not a derivation. This is not. This is just a notation for this expression. I copied this one in here. And complex conjugate is nothing but taking the transpose and then complex conjugate. So transpose is something to do with the flipping the left and right, bra and cat. So we can find this one is actually psi of x, and this one is a psi of x complex conjugate. And the complex conjugate and wave function, this product is absolute value of the wave functions squared. That's it. So this expression is compactly expressed in terms of Dirac's bracket notation. And this BZ notation is finally expressed as a very simple form if we assume that this integral is identity operator. So this is just our abbreviation of this notation. So what do you prefer? This one equals 1 is simpler, or this one is 1 is simpler. So Dirac introduced a very simple expression for expressing the quantum state in such a manner. And the corresponding matrix form is like that. This dagger is a kind of knife. This dagger represents transpose and complex conjugate. Transpose and take the complex conjugate. So I told you a few moments ago, this is just an identity operator, and this one in between this bra and cat, I insert the identity operator and replace this one as a wave function, and is a flipped one left and right side. This A stop, this kind of one complex conjugate is just nothing but this. So using this manner, this way, so original Max Born's expression for the square of the wave function integrated over the space is 1 is the probability of finding a particle all over the space is 100%, and that is simply expressed in Dirac's notation. And this kind of space is called Hilbert space, and it is comparable to the Euclidean space. And completeness relation that I already told you is to be explained. It's a dagger, that means a transpose and complex conjugate is nothing but to take the transpose and complex conjugate. If psi is C1 to Cn, then it's a Hermitian dagger, Hermitian conjugate or Hermitian dagger is row vector with complex conjugates. It is very similar to the case of Cartesian components in an Euclidean space. In Euclidean space, vectors are all real, so we do not take the complex conjugate. However, in quantum mechanics, just like what we have done with the electromagnetic field, it is convenient to use e to the I theta instead of sine or cosine. The wave function is easily described in terms of complex numbers. That's the reason why we have to take the complex conjugate too. We recall the Gram-Schmidt orthogonalization that separates a vector into a component that is parallel to a vector and another that is perpendicular to that vector. This the geometric idea is applied, can also be applied to a quantum state that is parallel to some state and that is perpendicular to some state. Okay, so using this idea, we can find the wave function can be expressed in terms of basis kets. And in here, all of the Euclidean vectors are describable as a linear combination of n basis vectors if we are in an n-dimensional Euclidean space. So in n dimension, we have components, and the components are to be multiplied to unit vectors that are all orthogonal to among one another. And this linear combination expresses arbitrary vector without missing any single one. That is, this expansion is very simple if we use the basis vector to be orthogonal and normalized. So scalar product of any two Euclidean unit Euclidean vectors satisfy the Kronecker delta ij. In a similar manner, we assume that any quantum state expressed in terms of ket that are expressed as a linear combination of basis kets. These basis kets are nothing but, you remember, if you look into the harmonics of a pipe, you remember the ground state and the excited states will give different frequencies. And the sound generated by an instrument, musical instrument, is nothing but the sum of sum of various harmonics, and each harmonic has its own amplitude. The sum of this wave is the resultant wave that actually being generated from this instrument. Quantum mechanics is nothing but the wave mechanics, so this one respects the same structure. In usual expansion of a Euclidean vector in terms of basis vector, we use this notation. However, if we make use of what Dirac's bra and cat notation, this one is simply expressed in this way. So when I want to find out the component, what I would do on the usual way is to take the scalar product with the vector with respect to a unit basis vector. In the expression using Dirac's bracket notation, it is simply this. So if we carry out further, any Euclidean vector is a linear combination of unit vectors, and each component is nothing but the scalar product, right? So we have substituted this one. We find this one, this k and k appear twice, and this is nothing but a number, real number. So I can change the order. So if I change the order, the expression becomes a very, very compact. And I need to sum over every component. But we began with the original vector x, end up with the original vector x multiplied by this complicated object. We conclude that this is x, identical to x. Any operator that acts on something that gives the same thing, what's that? That is the identity operator. Identity operator can always be constructed by adding all of these elements coming from the Cartesian basis vectors. Okay, so the first one is nothing but this, second one is this, and nth one is this, and if you add all of them is this. Sometimes you say it is a direct product, or sometimes you say outer product, whatever. This one can also be applied to quantum state, and quantum state is a linear combination of various eigenstates. Eigenstate means it has a distinct momentum or energy or any physical variable that we measure. And I told you quantum state is an can be expanded in terms of eigenstates, and then eigencat is a bracket notation for the eigenstate. And its eigenstate has its own physical value that is distinguished from anyone else. And these distinct values that are usually quantized, in that case, just like the Euclidean basis vector, this state cat satisfies the orthonormal relation that eventually relates to the completeness of the whole state. So Hilbert's space of a quantum state is nothing but the possibility of expansion of arbitrary quantum state in terms of well-known basis states that are usually called harmonics in musical instrument. All right. Now, we would like to consider a special case that is infinite potential well. And here, the wall is very hard and a particle is traveling around inside a one-dimensional well. So it is free in between the two hard wall. Free particle, it has the form e to the I kx minus omega t style. However, special case is the wave function must not pass this hard wall because the potential energy is infinite. In that case, the wave function outside must be zero because it is impossible to find a particle whose potential energy is infinite. Therefore, the wave function must be flat outside the wall, inside the wall. In between the wall, it is a free particle. Free particle is e to the kx minus omega t style. However, we know that wave function must not be broken. The only possible way of this kind of sinusoidal wave function, whose values at these 2 points are vanishing, is nothing but this. You have seen this one so many times. That is what? Vibration of string. Exactly the same way vibration of a string depends on sine function. This one is obtained by applying a simple argument, just like Snell's law derives from the fact that electromagnetic wave doesn't break. In a similar manner, we derive this. And finally, you will find this k runs from 0 to infinity. But when I substitute 0 here, wave function becomes 0. If a wave function is 0, then probability of finding this particle is 0. So the only possible way is natural number only, 1, 2, 3, 4, and so on. And they are found to be all orthogonal. And this derivation is already given when we study the wave mechanics on the vibrating spring. And Schrödinger equation is nothing but the equation of motion for this kind of wave, and the energy and momentum are well defined. And because the energy of this particle, its momentum of this particle is either plus or minus. It is a kind of standing wave. If I know the momentum, I can compute the energy of the particle. However, there are many possible values that are constructing the basis. We already have seen that there is a completeness relation satisfied by all of the available eigencats. And these eigencats generate the eigenfunctions. This equal is missing. Okay, so we have studied a little bit about the quantum state, especially a state isolated inside the infinite potential well.